Hi. Okay, let's go ahead and begin. Let me introduce everyone. Manfred Warmuth from Google Brain and UCSC. He'll be speaking on winnowing with gradient descent. Manfred was my PhD supervisor, great supervisor. For those of you who don't know Manfred already, lots of foundational work in machine learning theory and a lot of foundational work in online learning theory. Manfred, why don't you take it away?
Okay, thanks, Mark. And Mark was one of my craziest PhD students in a complementary way. So I'm going to talk about winnowing with gradient descent. And please ask questions, interrupt me. You know, I don't have to go through my slides. What's winnowing? You throw grain in the air to separate the grain from the chaff. And I usually do winnowing of soybeans because I'm into fermenting. So I crack the beans and then I blow off the husk with a blow dryer. That's the modern way of doing it. So what happens is Nick wrote this first paper when learning disjunctions when irrelevant attribute abounds. So essentially the chaff is the irrelevant ones. And he learned k-literal disjunctions with k-log n mistakes. That was started everything. And let me explain to you that winnow setting a little bit more. Let's say I have a 2 out of 5 literal monotone disjunction. Then I encode the disjunction as a bit vector. First and third variables are on, the others are off. Then you get an instance vector, which is also binary. And then you model the disjunctions as a threshold. If it's bigger than a half, then you say yes, otherwise you say no. And he studied this thing in an online learning context. You get a vector, you make a prediction, which is a plus minus 1 label, you get the feedback, and then you incur a loss, etc. Okay, you do this online thing. Okay, so the instances are in this domain, and the predictions are plus or minus 1. Okay, now, so here's the winnow algorithm. You start out with all variables being on, essentially 1, 1, 1 scaled. Then you receive the next instance, and you predict with a threshold. If your threshold of the instance with the current weight vector is bigger than theta, you say plus 1, otherwise minus 1. Then you receive the labels, and then you update. You update the weight vector. You believe in the individual components. Okay, here we go. So the fundamental piece that Nick invented was you use an exponentiated update. So the new weight is the old weight times e to the minus something, and this is going to be a gradient of a loss. And this funny update, this little algorithm, this is the beauty of machine learning, a few lines of codes, amazing things, makes at most k-log n mistakes, and k-log n is also the VC dimension of k-literal disjunctions. Okay, so there's a corresponding algorithm, the perceptron algorithm, which does an additive update. New weight is old weight minus a to the gradient. Okay, and this is actually the gradient of the hinge loss. So the multiplicative update always puts the gradients in the exponent. The additive updates has them at the same level as the weights. Now, multiplicative updates are a special case of mirror descent. Mirror descent, you have a link function, which is an increasing function, and then you say f of the new weight is f of the old weight minus a to the gradient, which can be rewritten this way. So you take your weight, with the f function, you go to the other domain, to the gradient domain, you subtract the gradient, and then you go back. Now, if the link function is the identity function, then you get gradient descent, which is this one. If the link function is the log, then you get, this is the multiplicative updates, you get log of the weights, new weights is log of the old weights, is the gradient. And then if you move this around and you undo the log, then the log is undone and you get this multiplicative update. Yeah? And there's also a normalized version.
Can I ask a question?
Yes.
Is the link function user specified?
Yes. That's a design question. So I'm going to basically talk about the two main ones, which is the log link and the identity link. And then I talk about translating the links into each other using reparameterizations. And that's sort of the new thing of this talk. Okay, so you can also have a normalized version. Then you just do the exponentiated update and you normalize. This is called EG. This is EG unnormalized. Okay. So there are two main families of updates. Gradient descent, which is the identity link. Backprop kernel methods belong to this family. And then there is the other family, which is Winnow belongs to these families, the expert algorithms, boosting, Bayes. This is sort of Euclidean distance squared regularization, and this is entropic regularization. You will see this in a moment. Okay, now, very often for sparse targets, this first family, the gradient descent family, its number of mistakes or, you know, the performance somehow grows linearly in n. Whereas the multiplicative updates, it grows logarithmic in n. So for the disjunction problem, the number of mistakes of the gradient descent family, which is the perceptron algorithm, it would be k times n, whereas Winnow was k log n. Okay, so we were very much fascinated by this difference. Okay, good. So here what we're going to do is we reparameterize EG and make it look like GD. And surprisingly, the reparameterized forms act like the multiplicative update. So we winnow with gradient descent, and previously thought this was absolutely impossible. Previously thought that there was a chasm between these two families, and there's no way to get the multiplicative performance, the log n performance, with additive updates. And it's quite a fascinating story. It broke my world, you will see. So here's, let's forget about threshold functions, a little bit too complicated, make it simpler. Fundamental problem, linear regression, sparse linear regression. So here is the instances, they are rows of a matrix, and this is the linear weight vector, and this is the target. So I'm picking out with this weight vector, the fourth component, right? First example is this row, -1. Third example is this row, -1. Last example is this row, +1. Everybody get that? So that's the simple problem. So the instances are, you get a row and a label, you incur a loss. Now here's the two updates again. Multiplicative, gradients are in the exponent. Additive, this one. Everybody understand this? It's a very simple paradigmic problem that I'm going to play with. Good. Now, there's major differences between these updates. There's again the linear versus log n. So what happens is, if you pick a random ±1 matrix and make the target be the first column, then here you have to understand these plots. So what do I plot here? I plot all 128 weights after training on 20 examples, the first 20 examples till consistency, the first 60 examples until consistency. So what happens is, this is the good weight. It's the weight of the first feature is picked up linearly, roughly. And the other weights linger around. The small weights linger around. And the red is the average loss at each of those points. So the average loss goes down roughly linear. Actually, we know the exact curve. It's not quite linear, but close to linear. For the multiplicative updates, it's dramatically different. The good weight is picked up exponentially fast. The other weights decay very fast. The average loss goes down extremely fast. Essentially, you learn after log n many examples. There's also a two-sided version of multiplicative updates. It's too much for a talk, but I can talk about that too. Okay, so the fundamental thing is, after half of the example, the error is still a half, roughly. Okay, good. Now, you can go ahead and make this matrix perfect. The rows are perfectly orthogonal. Then what you do is, the rows are from a Hadamard matrix. Okay, basically they make the rows perfectly orthogonal. That's the only difference there is. They're beautiful matrices. In that case, the loss goes down perfectly linear. The good weight is picked up perfectly linear. And the picture looks like this. Multiplicative updates, again, beat the hell out of things. This bound, I'm going to talk about a lot. It's 1 minus t over n. It's the linear, we call it the linear lower bound. For half of the example, the average loss is still a half. Okay? Questions? So what you should get now is you should understand additive and multiplicative updates. You should understand that there's major differences between the two. Okay? Good. Now, amazingly, when I showed this to kernel people, they says, well, why didn't you just add a kernel to gradient descent? But we proved that the linear decay of the loss, this lower bound, remains even if you expand the instances with an arbitrary phi map and run a kernel algorithm. So no kernel algorithm can beat this lower bound. In the argument, of course, you cannot fix a particular target. You have to average over targets. So on the average, the linear lower bound remains. It also remains in some sense when you have a sigmoid or a transfer function on top. So when we saw this, we conjectured, that was Michał Derzyński and me, that the Hadamard problem remains hard for any neural net trained with gradient descent. That was the conjecture. So if you take orthogonal instances or random instances, make the target to be a feature, sparse feature, which is the paradigmic problem, then no neural network trained with gradient descent can learn it. That was the conjecture. I'm going to break this conjecture now and fix it again. You'll see. So there were 3 stunning surprises. So continuous EGU can be simulated with a continuous gradient descent on a certain spindly network. You will see in a moment. And the discretized version of the continuous gradient descent solves the Hadamard problem efficiently. So the conjecture about gradient descent not being able to learn Hadamard problem efficiently was wrong. Okay, good. So we have a simple neural network that can crack Hadamard. So this actually shows that neural networks are significantly more powerful in special cases than kernel methods, which is, a lot of people have puzzled about that. We have the answer. Then we show that all we did is we kept the algorithm the same, but we changed the structure of the network. So the structure of the network sort of determines the implicit regularization. And then we actually proved, this would be the next talk, a linear lower bound for the Hadamard problem. It remains if you train with gradient descent, but you have a fully connected input layer. Okay, I'm not going to talk about that today. That's a separate thing. Okay, good. Now, how do we get to all of this? Well, the crux was we went to continuous updates. So we view the weights as a function of time, and then mirror descent becomes f dot link function dot. This is physics notation. Yeah, it's a derivative of this f of wt with respect to time is minus the gradient. Okay, the examples are still discrete. They sort of between different time clicks, you have a constant example. You can make it also continuous, but in the simplest case, we make it discrete. Good. Now the 2 main updates now are again the additive update. Which one? This is simply sailing down the steepest slope. It's perfect skiing. You go down ever so slightly to always the steepest slope. And now EGU has a log here. That's the difference. So we're now going to do all of our motivations and kind of thinking and beautiful visualizations a little bit in the continuous case, and then do discretizing at the end. And this kind of was a very powerful tool. I tried to do this years ago with Arun Jagota, only partial success, but now we went further. So what's happening? What did we get with this kind of thinking? Well, we did the following. This is the normal linear neuron. And if you train it with gradient descent, you have this lower bound. You see that picture on the right, this little lower bound. It goes down linear. After half of the examples on Hadamard, error is still a half. Average error is a half. Good. Now we have a new network, that's spindly network. The spindly network takes the edges and replace them by double edges. Right? So I reparameterize wi as ui squared. If ui is initialized equal, they stay equal. Okay, and now we show that continuous gradient descent on the ui is exactly as continuous EGU. So in math, this is continuous gradient descent on the u, right? So what happens here is it's a continuous update, you see? The gradient is a little bit more complicated because of the chain rule. You get another u out here. Okay, good. And this one simulates precisely this update, which is the multiplicative update with the log here.
What's the difference between the dot and the dot with the circle?
Ah, good. This is derivative with respect to time, and this is Hadamard product, components-wise product.
Like the dot product?
No, the dot product sums, and this one just, so if I take u circle dot u, it's another vector with the components ui squared.
Okay, okay. And then the dot
it's called the Hadamard
that,
product, huh?
And then the dot after that is the dot product.
That's the normal dot product, yes.
Okay, okay.
Yeah, it's just a concise way of writing it. Yeah. Yeah, it's just a concise way of writing. I can write it component-wise. Then it would be u dot I, and then it would be ui squared. And now you have to still use the circle dot. Yeah, it's just a concise way of writing it.
Okay, thanks.
Good. But you can kind of see what's happening is, if you look at the prediction to explain it, the prediction is, this is the prediction here, the y hat. The prediction is ui squared times xi summed. Right? And here it is wixi summed. Right?
Well, another question, Manfred. Is it obvious that is there an intuition why the UIs stay equal to one another without being clamped?
Yes, you will see this in a moment. It's a fascinating thing. Yes, exactly. Okay, good. So we now do it with different U's and V's, and it has actually advantages. But initially, the simplest thing is if you make them the same, initialize them the same, and then they stay the same. You will see. Good. So the discretization. So here's the continuous case. Then you can discretize the updates. Right here they are equal, but here when you discretize them, the updates, then they only track each other. We did simulations, of course. We ran EGU, and then we run EGU as GD. Right, this is this reparameterization, and it looked the same. But then we went into the simulation and looked at the second and fourth order precision, and they're not the same. Okay, but so they're visually identical but slightly different numerically. But we were able to prove the same regret bounds so when you prove bounds, you can prove the same bounds for this as for this. So that was just kind of totally surprising to us. So we can actually prove that on worst case data, adversarial presentation of the data, this simulation, the reparameterization, cracks Hadamard efficiently. Okay, now let's just talk about this initialization and so forth a little bit. So here's this funny network. We call it spindly. if you, so it cracks Hadamard, even in the discretized case. Now, if you add all the red weights, you make it a complete layer, and you initialize the red weights to 0, then you can show that it has linear loss when trained with gradient descent. The picture looks essentially like this again. So also you can initialize all the bottom weights to 0, it still looks like that. So what happens is gradient descent gets confused if you add all the edges. Okay, good. But it's not just a matter of initialization. This one cracks Hadamard. When they all initialize to 0, you still have the linear lower bound. Okay, good. Now clamping, this is what Mark was hinting at. Here is again the linear lower bound. But if you do the gradient descent update and then clamp the gray weights to 0, then suddenly you're in this situation. So you can do your gradient descent update, and then just all those weights that are off diagonal, if you set them to 0, then suddenly you're in this situation. It's bizarre. Now, let me talk about the other thing that Mark was hinting at. So here's a UI. If you initialize them to be equal and do gradient descent on the weights, they stay equal. So you do not have to enforce the clamping. It just happens automatically because the gradients are the same.
Manfred, sorry to interrupt again. Is that stable? If I jiggle one of the weights a little bit, will they start to get out?
No, it's stable. It's very stable. Actually, it is beneficial to work on with different weights. It can get the two-sided versions automatically. If I set the top layer to 0 and the bottom layer uniform, then I can learn positive and negative weights, targets. It's very interesting. We haven't written that one up yet. Okay, this is confusing me because I cannot scroll. Okay, but I will survive. So what we showed is that if you take this network and if you do the continuous updates, you can show that it converges to the smallest L1 norm solution. And if you add these additional weights, you go to the smallest L2 norm solution. This is kind of a style proof that was introduced by Nati Srebro and Surya Gunasakar. I'll mention that briefly. Okay, so then if you have a neural network, you can go ahead and replace the local weights by the spindlification. If you want a two-sided version, you have to do this trick, but we recently simplified that. But anyway, you have to do some kind of local replacement, and then you automatically have, you can run gradient descent and you implement the multiplicative update. Good. Now let me show you these simulations. So we don't just do multiplicative update in terms of gradient descent. We did it the other way around. So this is gradient descent. This is gradient descent two-sided. This is the multiplicative update two-sided. Here's the one I talked about, that's spindly. EGU as gradient descent. You can do it also two-sided. You can even simulate gradient descent as a multiplicative update, but then the approximations are not as good for some reason. I don't fully understand that. For that, we didn't prove bounds. But we have a general theory how in a continuous case you can simulate one mirror descent algorithm by another mirror descent algorithm. I will explain that theory today. Okay, so now how much time do I have?
29 minutes.
How much?
29 minutes.
Okay, let me skip the kernel stuff a little bit because it's a bit much. Okay, good. Okay. So how did we come up with this? Our work was triggered by a paper by Gunasakar, Nati Srebro, and a bunch of others. They show that the quadratic reparameterization converges to the L1 norm solution in the unconstrained case, and they generalized it to the matrix setting. Now, this reparameterization, however, was already known to a large extent by the game theorists in 1979. There's these papers. It's a totally different language. It's even very hard for me to understand it because it's different language. It comes from evolutionary game theory, why the multiplicative update is related to the replicator dynamics of evolutionary game theory, the normalized one, e.g. So they analyzed this to a large extent, and they were into doing it everything with differential equations, and so they ran into these reparameterizations. Okay, all this previous work was done in the continuous case. We have the tools of the regret bounds, and we actually showed that discretizations track in the discretized case. You still the updates are still close to each other. And now, all of this work, we first futz around with Maple, MATLAB, all kinds of simulations. Then eventually we come up with bounds. You know, we have to give a lot of credit to these packages. I don't know how all the previous mathematicians did research. I have no clue. Well, that's how we do it. We futz around late at night when our brain is shot with these packages, and then we get bounds, and then we eventually prove it. Okay. So I want to give credit to these packages. Okay, motivations of the updates. I'm now going to motivate the discretized updates and the continuous updates and so forth. And that's kind of an interesting story. So we regularize with Bregman divergences. Okay. And then we motivate the updates, and then often we go from the continuous to the discrete. So what is a Bregman divergence? Well, Bregman divergence is, and that's Mark's thesis, he worked on this a lot. It's a convex function minus the linear approximation. And I give you the main examples in a moment. And always the little f is the derivative of the convex function. So hopefully Mark pounded this into you already. Okay. There's duality, there's all kinds of beautiful things. These are the dual parameters, and you can flip the divergence. So here's it's in the primal, here's in the dual. This beautiful math, very basic math. Okay, so now how do I motivate updates? You take a Bregman divergence plus a loss, and you trade them off against each other. This is sort of the inertia term that makes you stay close to the previous weight vector. And then this is the loss on the current example. And then when you take a derivative of this, you get this update. When you solve, you get the following implicit version. The new weight is, you know, the mirror descent, but here you have also s plus 1. So it's the gradient at the future at the updated weight vector, which you usually cannot do. So you approximate this by the old. We call this implicit and this explicit.
What's the derivative with respect to the old weights, WS?
Yes. So when you minimize this, then you get an equation setting it to 0. So at the updated weight, the gradient of this argument has to be 0. So the gradient here is at the updated weight.
Okay, yeah.
When you solve, you get what we call the implicit update. You have s plus 1 here and s plus 1 here. Nobody does this because it's hard to do, but this is the principled update. My conjecture is this beats Newton. It's really the right update. Then we approximate this update using the old gradient, and then all hell breaks loose and it's not good, not as good anymore. Okay, good. But good enough in many situations, of course. In the continuous case, you don't have this dichotomy, right? So this is just something that comes from the discretization, this issue of explicit versus implicit. So here's the continuous update. Okay, good. Here's the main examples. Again, the link function is the identity, link function is the log. Now, we also interpret it between these two. So for that, we introduce a log tau, which is sort of a polynomial approximation of the log. But then you can change tau. And so here's the curve. This is tau equals 1, which corresponds to the EGU. And tau equals 0 corresponds to gradient descent because it's a straight line. And this is in itself a very interesting topic. Goes back to Nautz, a physicist. If you look at the corresponding Bregman divergences, you end up with this thing. Okay, it's a bit of a salad, which you might not. This is the convex function, and this is the Bregman divergence. Good. But what I want to get across here, if you now change the tau parameter, for 0, you get normal Euclidean distance squared, which is what motivates gradient descent. For half, you get something interesting looking. For 1, you get the entropy. For 3 halves, you get something interesting. You get all of machine learning by changing this parameter. These parameters are also sometimes called alpha divergences. I think they're very interesting. So Bregman divergence with temperature is a very, very powerful tool. Okay.
Can I ask a question?
Yes.
So right now you have a single parameter on a linear scale. Can you say anything? What's the significance if I use something at the -1 end versus the 3 end? What's going on?
I don't know.
What does that job do?
That's your job. Look, I know this curve. We work between these two, and there's many open problems. We didn't even go to negative. It still stays increasing, but it bends the other way. If you do minus, the curve bends the other way. It's a very deep thing. Yeah. Put a bunch of PhD students on it. Okay. So how do you motivate updates in the continuous case? Well, you do the same thing. You just work with what we call a Bregman momentum. It's this Bregman divergence derivative with respect to time. If you minimize this, and then you need to do a little bit of variational calculus, which I didn't know, which I still don't fully understand, but it's magic. Then you end up with the update, the f dot update. F dot equals minus the gradient. Okay, so it's beautiful that it works out. Okay, so the motivation on the motivational level, it also works out. Good. Now you can also add constraints. The typical constraint is that the weights have to sum to 1, and then magic happens, projection matrices appear. You get the FW dot equals the projection matrix onto the constraint times the gradient. You project the gradient. It's very beautiful. You also see implicit versus explicit update. When you discretize this f dot equation, you can do Euler. If you do Euler approximation, you end up with the explicit update. You have s plus h, and here you have the s. If h equals 1, you get the usual thing. Now, you can, if you do a forward Euler, which is known by the people who do differential equation solving to be better and more stable, then you end up with this. This is the implicit update. But there's actually a better one. You will see in a moment. So the right way to discretize is you start with your continuous update, and then you partially solve this differential equation. You integrate. And if you do this, you get an integral of the gradient. Bizarre. And this is what we are trying to understand now and use as our main motivations for deriving updates. So this is the correct way to discretize. If you go ahead and approximate, so this is without constraints, and then with constraints, there's just simply a projection matrix in there again. Beautiful. Good. So what you can do is you take that integral, and if you approximate it by a box where the length is there's different ways of approximating this integral. You can use the last gradient or the old gradient. So if this is one box and this is the other box, so you get two different approximations. You can kind of see that the explicit update is one approximation of the integral and the implicit one is another one. The true one is really this one. This is typically better than this one. Okay, good. Other beautiful things. We have this Legendre transform whenever we work with Bregman divergences. There is a dual update, which is this one, right? This is what we call the dual update before. Good. And then you can rewrite it in the other way. And you can undo this f dot and move it over, and then this update looks like a continuous natural gradient update. Also interesting. And this also works with projections. The projections come like this. Okay, so what I wanted to talk about is a particular case now, to give a little bit more of a feeling, and you see immediately run into open problems. Everything is trivial with gradient descent. You can even sometimes solve the equations. So here's the simple paradigmic problem we started out with: square loss, linear regression. Okay, and this is the dot update, gradient descent. Right, it's written in matrix form for fun. Good. And now it turns out you can solve this. Okay, if you took a course in differential equations, the first course, then you would be able to solve this. I of course skipped that course. I didn't take many courses. So anyway, so you can learn this. You can solve this. Now for EGU, the differential equation is very similar. It's this one, or the continuous, or you can, in the continuous one, it's the same to the other one, to the gradient descent with the reparameterization. And here's the update. But it's implicit, I and I, WI, right? Or this is, if you write it using the circle dot, the O dot notation, which was caused confusions before, it becomes this equation. And we don't know how to solve this. And also we don't know how to solve it in the intermediate case we're using, if we use taus to interpolate between. But the simplest case of multiplicative updates, we already don't know how to solve. If you know how to solve this equation for me, I will kiss your feet. Okay, try. I don't know how. Very frustrating. Okay, so you make a leap, you go forward, and then you're stuck again, run into a wall. So this is our favorite wall or unfavored wall. So now let me talk about this, what these things converge to in the continuous case. This is important to analyze. You can kind of show that if you do this, the tau version with linear regression, and you have a bunch of assumptions and it's kind of annoying, then you can show that you converge to the smallest L2 minus tau solution. So you remember, you're in the under constrained case. You see half of the examples, there's still a lot of solutions. You want to know what your update is up to, what is it converging to? It turns out gradient descent converges to the smallest L2 norm solution, and the multiplicative update, the smallest L1 norm solution, and in the middle, tau norm interpolate. So this is kind of interesting to know. These techniques were pioneered, that we learned them from Surya and Nati et al., right? That paper that I referenced. In some sense, for a cold person, this is not interesting because it's not discretized updates, but it's still informative because it shows what the update is after. Yeah. Questions? Okay. I blew everybody away. Okay. So now I'm going to do, Mark, you still there?
I'm still here, Manfred. I kind of had a small question there, which is more a speculative question. Yeah, go back to this slide. So anyway, insofar as I understand what you've presented so far, one bit of your idea here is that you've identified some class of updates parameterized by tau related to Salas entropy, and what you've observed is in the continuous case how things converge to something that looks like some given regularized solution, like with the L2 minus tau.
Yes. Yes.
Now, of course, you introduced the Bregman divergences originally, and when Bregman introduced the Bregman divergences, this was as a method to solve, basically to find regularized solutions of, you wanted to find, what did you want to find? You wanted to find the minimal, suppose you had a convex constraint set.
Yes.
You wanted to find the point in the convex constraint set with the minimum value of some given convex function f. That convex function led to the Bregman divergence f. So you know, you kind of have a parallel in results there. Is there any? Sorry, this is kind of speculative nonsense.
Yeah, but the thing is, all I want to say, yes, these people observed this before, and the original motivations does this. What I'm saying, everything becomes clean if you go to the continuous case. In the continuous case, it's exact, and then when you go to discretization, it gets confusing. But we have this new tool which Bregman didn't have, regret bounds, and we show actually it is happening. That's the point. So what I'm showing next is I'm going to show the reparameterization. Okay, it turns out that if you have an update that uses an F-link and a G-link, how do you translate them into each other? So in other words, you want GU dot with a reparameterization function simulates F dot. And all you need to do is check a condition on the Jacobians. This proof is trivial. It's not suitable for a talk, but the proof is not hard. If you know how Jacobians work, which I forget each time. Okay, good. I'm going to just do it by examples. So the reparameterization, the simplest one is u dot u, the square one. Forget about the constants, not important. You can go the other way. It's 2 times square root of w. And now you check your Jacobians, they're the same. What that means is that log dot is equal to u dot, you see? And here you see the reparameterization, the square. Okay, so this is sort of a general trick. I give you other ones just for fun. You can simulate Burke, which uses this link, but then the reparameterization is an exponential. You check again your Jacobians, it's the same. And what happens is that the Burke continuous update, or it's also Itakura Saito, can be simulated with gradient descent this way, where you have an exponential sitting in there. Bizarre. And you can do the log tau update, which is this one. Looks messy. You can write it as the link is the log tau link, right? The Q function happens to be this. And now it turns out that the log tau update is a gradient descent update with this reparameterization. With a graph, it looks like this. You double the edges, but you put a power on there. And if the power is, if tau is 1, you get the spindly, the fundamental spindly. If the power is 0, you get square root, and square root becomes again u, and you get the normal gradient descent. It's just magic. Good. So this is the reparameterization trick. Who cares what happens in the continuous case if the continuous case doesn't simulate, doesn't track in the discretizations, but using regret bounds, you actually can prove that. So I'm going to do now a summary of the updates, and then I talk a little bit more about the regret bounds at a high level. So this is the case, not now in the linear regression case, because it would be too complicated to write. I do it in the dot loss case, like the hedge loss. This is EGU. Then there's prod U. And this is our simulation already. It looks like this, looks very similar, but there's a little subtlety, as you will see. Actually, to compare it, what you need to do is you need to square things. Okay, because it has this square reparameterization. This is Hedge. This is the approximation. It's the Taylor approximation. There's prod U. This is the normalized simulation of the multiplicative update of EG. And what you can kind of see is there's these factors, and then there's always the exponential. And actually, what this simulation, the spindly update, is after is this update. The spindly update is this. It's e to the, and now you need to put an eta over 2. And if you do it twice, you get this. In other words, essentially, the spindly update is sort of half an update with learning rate half. Quite interesting. But the exponential factors are still, which come from mere descent, they are more principled. Why? Because if you take update L1 followed by update L2, you get update L1 plus L2. This is not true if you do the reparameterizations. So this one, which was spindly, is fundamentally flawed in the sense that it's not commutative, whereas this one is still. So this is memoryless, commutative, has all the beautiful motivation, but this one is, it is really an approximation. It happens to be a good approximation, but it is an approximation. Questions? Good. Now I do talk about regret buttons at a high level. The total unline loss of the update minus the total unline loss of the best comparator is usually less than norms times square root of the loss of the best. We did these regret bounds for the simulations, for the reparameterizations. EGU as GD hinge loss, we proved the same regret bound as for Winnow, for linear regression, same regret bound, all the same regret bounds. We redid the old proof. We didn't come up with new proofs, but we just did exactly what the old ones were. And the fundamental problem or interesting fact is that we use reparameterizations, but we still use the relative entropies in the proofs as a measure of progress. So we don't use gradient descent, and this is a total puzzle. So gradient descent measure of progress would be Euclidean distance squared, but we don't use this as a measure of progress. We use the relative entropy, and we're totally puzzled by that. Okay, so there's many open problems that we have. I'm going to finish quickly. For instance, is there a natural problem for which gradient descent beats EGU plus minus? For instance, gradient descent is hard to implement with chemicals in the brain because you switch from positive to negative gradients. The multiplicative updates in some sense can be simulated. And but not that I know anything about it, but I'm fascinated by this. The question is that intuitively, the brain must take advantage of these multiplicative updates. It cannot do gradient descent. So the question is how it does it. And anyway, there's beautiful questions there. Solve the differential equations for EGU, regret bounds for the log tau update. We don't have that. Revisit vanishing gradient issue, batch normalization, dropout, all these kludges that were done for gradient descent. What are they for EG plus minus? Do large scale simulations. And then the second part, does any G-trained neural network with a complete input layer satisfy the linear lower bound? We have done this already. Now, there was an alt paper on this year. And now I skipped over this because it was too much. We have somewhat the optimal kernel, and we're writing a paper on this. So this is pretty much it. And here are some papers, and all my papers on this website.